You've seen previously how augmented matrices can be used to solve a system of linear equations. There are other uses of matrices, and we're actually going to see how to use matrices to solve linear equations. To understand matrices, we first want to understand matrix multiplication. Now, there's some details about matrices that I'm not going to cover here. I'm going to be mainly focused on matrix multiplication, but you can also do matrix addition, and it's very simple. Matrix multiplication is simple, but I won't say it's very simple. You just have to remember the rule. So to start, this thing in brackets that I've got here, a left bracket, a 2, a 4, and a right bracket, okay, that's a row matrix. It's two numbers in a row with a square bracket on the left and a square bracket on the right. That's what we might call a row matrix. I mean, it is a row matrix. So, but right now we'll just call it a row. Okay. In a column is similar, except the numbers are in a column. They go up and down. Okay. So the column we have here consists of the numbers -3 and 5. -3 at the top, 5 at the bottom, with a square bracket on either side. Okay. And those square brackets are longer because you want them to be as long as the column of numbers. So we want to multiply the row 2, 4 by the column -3, 5. That is, the row consists of numbers 2 and 4 in that order. The column, top to bottom, consists of the numbers -3 and 5. To multiply that row by that column is very simple. You take the first number in the row, multiply it by the first number in the column. 2 is the first number in the row, 3 is the first number in the column. So you do 2 times -3. And then you do the second number in the row times the second number in the column. That's a 4 times 5. And you add that to the result you got from the first multiplication. So that the row 2, 4 multiplied by column -3, 5 is simply 2 times -3 plus 4 times 5. You do the arithmetic, you get -12 plus 20 equals 8. Now, there are many interpretations that can be put on this sort of thing. But we're not going to go very deeply into those interpretations. Very relevant to multivariable calculus and physics and stuff. But right now, we're not going to talk about that. Okay. Now I've got another row in a column here. And you see that there are more numbers in the row and more numbers in the column than there were in the first one. So I want you to take a look at this and think about it. Okay, the row vector consists of a left bracket, then the numbers 3, -6, 9, 1, followed by a right bracket. Okay. The column consists of a big long left bracket and the numbers -4, 2, 3, 5 in order from top to bottom, and then a right bracket. Okay. How would you multiply those? See what you think. Take a minute, ponder it. What did I do to the first one? What do you think would be an operation that corresponds to the operation I did for the first one that corresponds to the second one? Okay, well, you've had time to think about it. The answer is pretty simple to multiply these two matrices. You start by multiplying the first number in the row by the first number in the column. Okay, so that'd be 3 times -4. And just like before, you multiply the second number in the row by the second number in the column. That's -6 times 2. So you add -6 times 2. But then you've got a third number in the row. What in the world are you going to do with that? Well, by now, the pattern should be becoming somewhat so. You multiply the third number in the row by the third number in the column. Okay, so that's going to give us 9 times 3. And then we've got a fourth number in the row and a fourth number in the column. Fourth number in the row is 1, fourth number in the column is 5. So we get 1 times 5. Now you do all that. Let's see, we get negative 12 here, and negative 12 here is negative 24. Then we add 27, so now we have 3, and we add 5. We have, oh, coincidentally, this comes out 8. Same as our last calculation. I made these numbers up at random, so I wasn't planning that, but every once in a while there's a little miracle that occurs, isn't there? Okay, now let's do this third one. What do you think you're going to do with the row vector 2, negative 4, 6? It means bracket 2, negative 4, 6, right bracket. Okay, and the column 2, 3. In other words, left bracket 2 above 3, right bracket. Okay, now if you're a little confused about what to do here, I mean, it starts out pretty simple. You think, okay, first number in the row times first number in the column is 2 times 2. Second number in the row is negative 4. Second number in the column is 3. So we add negative 4 times 3. And the third number in the row, and the third, there's no third number in the column. What are we going to do about that? Well, if we don't have anything to match up with the third number in the row, we can't do it. So we try 6 times, nothing there, nothing there. Can't do this. Okay. Well, matrix multiplication is only defined if the row and the column have the same length. Okay. Here, the first example, we had a row of 2 and a column of 2 numbers. Second example, we had a row of 4 numbers and a column of 4 numbers. Third one, we have a row of 3 numbers and a column of 2 numbers. They don't match up. Okay. So times column define for a row and a column but when they have the same length, then it's very easy to do the multiplication. Now, if you have 486 numbers in the row and 486 numbers in the column, that's easy, but very tedious. And you're almost certain you're not going to get through that if you do it by hand without making an error. And at that point, you would use technology. Okay. Now, a matrix can consist of any number of rows of equal length. Okay? Say matrix has one or more rows of equal length. Example. Here's a matrix. It has a bracket on the left, a bracket on the right, and the bracket is high enough that it covers both rows. We have a row consisting of 2, 4, 3 at the top, and under that, a row consisting of -6, 9, 1. So that's a matrix with 2 rows and 3 columns. Okay, the 2 is the 2 in the first row is above the 6 in the second row. That makes a column 2, -6. And you have a column 4, 9. Second number in the row, second number in the column gives you a column 4, 9. Third number in the row, third number in the first row, third number in the second row gives us column 3, 1. Okay. This is called, it's 2 rows, 3 columns. So we say the dimension is 2 by 3, the number of rows by the number of columns. We write dimension is 2x3, 2 times 3, 2 by 3. We read it as 2 by 3. It looks like multiplication 2 times 3, but we read 2 by 3. Okay, now you could have a 10 by 47 matrix. Okay, it would have 10 rows, and each row would have 47 numbers in it. Okay, we're not going to do any of those. Again, you don't deal with those matrices by hand unless you really want some practice. Because you can pick it up by using just small matrices, and then you know what you would do with a larger matrix, even though you don't have time to do it. Now, let's multiply a matrix by a column vector. And I call it a column vector. I'll often use the word column vector because that's a very common and appropriate terminology. Matrix times column. Let's take the matrix we just wrote down. Matrix with first row 2, 4, 3. In the second row, -6, 9, 1. I'm going to multiply that by a column, 4, -6. Okay? Now, think, what would you have to do if you wanted to multiply this matrix with 2 rows by this single column? Give that some thought so that when I tell you, you have the advantage of having thought about it and maybe even thought about it correctly, which makes you feel good. So give it some thought. What's the most obvious thing we could do if we know how to multiply rows by columns? Okay, well, the answer to my question is you multiply the first row by that column and you multiply the second row by that column. Nothing more complicated than that. There are all kinds of complicated things you could do, and you could think of any number of procedures, but we multiply the first row by the column, multiply the second number by the column. So we multiply the first row by the column, 2, 4, 3, multiplied by 4, -6. That equals 2 times 4 is 8. 4 times -6 is -24. 3 times 4 is 12. That's -4. So the first row times the column is -4. Second row times the column is the row -691 multiplied by the column 4 -6. And you know what I'm doing here, it makes no sense at all. I'm not even sure how I did manage to multiply this row by the column because there are only two numbers in the column. Okay. So, you know, everything I've done here is wrong. So let's see if we can fix it. Didn't even seem to notice on the first row. I went ahead and did it. But I didn't follow the rule. Okay, so let's follow the rule and see. Let's say we got 4, 6, -2. That's going to be better because now when I try to multiply the first row by the column, it's going to work. And whatever I did last time just wouldn't happen. Here we have 4, 6, 2, 2, 4, 3 row by the column 4, 6, -2 equals 2 times 4 plus 4 times 6 plus 3 times -2. That's 8 plus 24 minus 6, which, if I'm doing my arithmetic right, is 26. So that's the first row times the column. We're multiplying each row by the column. Second row by the column. Second row is -6, 9, 1. We multiply that by the column 4, 6, -2. We get -6 times 4. First row number in the row, first number in the column. Second number in the row, second number in the column is 9 times 6. Third number in the row times the third number in the column is 1 times -2, giving us -24 plus 54 minus 2, which is -28 plus 54, which is 26. You know, all kinds of coincidences. Um, this came out 26. The last one came out 26. We got a couple of eights over there, and no pattern, no intent to do this. Okay. Now, we don't normally write out the first row times the column and then the second row times the column the way I've done. Because what we get when we multiply this is another matrix. Okay? So they don't have room to write it here, so we'll expand a little bit. Okay, the matrix product, I say has the result, and I've got to backtrack and say is a matrix. With two numbers. row one times column one, the first calculation we did, where we got 26. It'll go in row one, column one of the product matrix. Row two times column two, and it's not times column two, it's times column one. There's only one column. Row two times column one goes in row two. One of the product matrix. So the product matrix is I'm debating about how to say this, whether just to write out the product matrix or to lead up to. I'm just going to write it out. So the product matrix will be 26, 26. Does that fit the pattern? We say row one times column one goes in row one, column one. Okay. Here's a matrix. Here's row one. And here's row two. And here's column one. Okay. So this is row one. To the column matrix, 26, 26, 26 above, 26 below. Row one is a very short row. It has only 26 in it. Row two, very short row with only coincidentally 26 in it. Now wait a minute. Got my numbers mixed up. A little inconvenient having two 26s. And somehow I got the product 28 and I won't say what happened in my head. One of those things you just don't want to know about. Okay. This gives us 28, not 26. So row one times column one, this is row one times column one, gave us 26. Okay, when we calculated row two times column one, we got 28. So when I write the product matrix, it's the column 26, 28. Okay. Now again, row one of our column matrix, column vector is 26. Row two is 28. There's only one column, so it's column one. Is the column. 26 is in row one, column one. 28 is in row two. Column one. That's your rule. Now we're going to do another matrix product. We're going to multiply a matrix with two rows. This matrix will be 2, 3, -4, 5, -1, 3. And we're going to multiply this matrix by the matrix with two columns. Okay. Previously, we multiplied the matrix with two rows by a single column. Now we're going to multiply a matrix with two rows and three columns by a matrix with two columns. Okay. Now, the columns have to have length that matches the rows. So each column is going to have three numbers in it. Otherwise, we can't multiply a row by a column. So let's just put some numbers here. 3, -1, 2, and -4, 3, 5. Okay, so our first matrix, two rows. First row, 2, 3, -4. Second row, 5, -1, 3. Second matrix, two columns, 3, -1, 2, -4, 3, 5. What's this equal? Well, think about it for a minute. What are you going to do? How many ways can you multiply a row by a column? Okay, well, hopefully you've thought about that. Okay. Well, you can multiply the first row by the first column. You multiply the first row by the second column. Or you multiply the second row by the first column. You multiply the second row by the second column. Following what we did before, if you multiply the first row by the first column, the result has to go in the first row and first column of the product matrix. Now I'm going to write row 1, column 1 up. Okay, in my new matrix, in the upper left-hand corner, I wrote R1C1 for row 1, column 1, because that is in row 1 of the product matrix, and it's in the first column of the column matrix. Now below that, we write row 2, column 1. I'm just using R2C1 for row 2, column 1. Okay. Now, that is row 2 and column 1 of my new matrix. Okay. And row 1, column 1 corresponds to multiplying my first row, 2, 3, -4, by my first column, 3, -1, 2. Row 2, column 2 corresponds to multiplying row 2, 5, -1, 3, by column 1, 3, -1, 2. And again, row 2, column 1 is in row 2, column 1 of the new matrix. Then we can also multiply row 1 by column 2. And that goes in row 1 of the new matrix. Right across from row 1, column 1, we got row 1, column 2. And it goes in a second column because it comes from column 2 of the second matrix. So we're starting a new column. So in the upper right-hand corner of our new matrix, we're going to have row 1, column 2. And in the lower right-hand corner, we're going to have row 2, column 2. And that's going to come from the second row and the second column. Yeah, it's going to take a little room to write this out, but I'm going to write it all out. Okay. First number we need is row 1, column 1. If we multiply row 1 of the matrix, 2, 3, -4, by the column 3, -1, 2, we're going to get a number. Now that number is calculated, and I'm going to write the calculation down here. Okay, so in the upper left-hand corner of my new matrix, okay, I've got it. I'm starting a new one now. Where we're going to have row 1, column 1. That's 2 times 3 plus 3 times -1 plus -4 times 5. Now that's a lot of numbers, but that is just an addition of 3 products. And when we do the arithmetic, it's going to be a single number and it's going to go in the upper left-hand corner of the matrix. And then row 2 times column 1, 5, -1, 3, that's row 2. Column 1 is still 3, -1, 2. So we're going to get 5 times 3 minus 1 times -1 plus 3 times 2. Uh-oh. I got to watch my eyes. The first row, first column, we have 2 times 3. First row, first number in the first row, first number in the first column. And 3 times -1, that's good. And then we have -4, and I wrote -4 times 5 because my eye picked up the 5 in the second column. It should be -4 times 2, and I hope you picked up my error. Okay, so again, first number in the, okay, first row, first column product, 2 times 3, 3 times -1, -4 times 2, not -4 times 5. Okay. When we write out the second column, well, it's as I said, 5 times 3 minus 1 times -1 plus 3 times 2. Now we go to the second column. Okay. Over row 1, column 2, that's going to be in the upper right-hand corner of our new matrix. And that's going to be 2, 3, -4 multiplied by -4, 3, 5. That's going to be 2 times 3 plus, no, I'm looking at the first column. Okay, my eyes just aren't going where they need to. I got to focus a little better. I apologize. Okay, let's try it again. As a matter of fact, pause for a minute and you write out the result. Multiplying the first row by the first column. 2 times -4, 3 times 3, -4 times 5. Write that out. Now, you've hopefully taken time to write that out, and you can check me. Okay, that's 2 times -4 plus 3 times 3 plus -4 times 5. Checking. The first number in each product should be the first row. 2, 3, -4. First row is 2, 3, -4. Second number in each of these 3 products should be the number in the second column, which is -4, 3, 5 when I look down here, -4, 3, 5 when I look up here. Okay, so I've got that. I really am making these mistakes. I'm not just tending to make the mistakes to illustrate how you make sure you've done this right. I'm just doing it wrong. Okay, my eyes not looking right. Okay, anyhow, second row times the second column, we got 5 multiplied by -4 plus -1 multiplied by 3 plus 3 multiplied by 5. Now do that independently, make sure I've got it right. But I can see in the, I can see the 5, -1, 3, which matches the second column. And the -4, 3, 5, -4, 3, 5 matches, I'm sorry, the 5, -1, 3 matches the second row. The -4, 3, 5 in my product matches the second column. Got to be careful when you do these. Okay. Now I do the multiplications. 2 times 3 is 6. 3 times -1 is -3. 6 minus 3 is 3. And then times -8, which gives me -11. 5 times 3 is 15. -1 times -1 is 1. That gives me 16. 3 times 2 is 6. That gives me 22. Check me on this. 2 times -4 is -8. 3 times 3 is 9. That leaves us 1. And then -4 times 5 is -20. So it leaves us -19. And 5 times -4 is -20. -1 times 3 is -3, gives us -23. And 3 times 5 is 15. -23 and 15 is -8. Now, I did that kind of fast. There's a significant chance that I made a mistake, but I kind of think I got them right. You check my numbers. Do we understand the process? We multiplied the first row by the first column and ultimately got -11. That goes in the first row and first column of the product matrix. We multiplied the second row by the first column, and we got 22. And that goes in the second row of the product matrix in the first column. And then we multiply the first row times the second column. I got -19, make sure I'm right. And that goes in the first row, second column. And then the second row times the second column gives us -8. That goes in the second row, second column of our matrix. Now that's a process of matrix multiplication. It's that simple. You'll see other examples in open math in your homework, etc. And you can see as many examples of matrix multiplication as you like, if you go to the reliable website. I would not let AI generate a bunch of matrices and give you the answers. Right now, at least AI is pretty unreliable with arithmetic because it's not really doing arithmetic. It's trying to figure out what the next word is, the next number, and it doesn't do it by actually multiplying the numbers. I'm not sure exactly how that works, but it's a large language model. And at this point, it doesn't work very well. Now, if you look, if you're viewing this a year from now, so if this video is a year old, AI is probably going to be much better. It might well be good at arithmetic by then. There'll be other things you can't trust it for, though. All right, that's matrix multiplication. You should be able to multiply any matrix. So I'm going to give you one and ask you to work it out. And let's say we got okay, this matrix has 2 rows. First matrix has 2 rows, 2, 3, 7, 4, -1, 5. Second matrix has 3 columns, 1, 3, 2, 2, 1, 3, 3, 2, 1. First of all, how many rows and how many columns is the product matrix going to have? Want to think that through, but then fill them in, okay? Fill in the products and see what you get. Now, when I do this, I'll write it out quickly. So be sure that you've worked it first so you can tell whether I'm writing them out correctly. Okay, hopefully you paused and taken the time to do all this. First place, the first row can multiply the first column, the second column, or the third column. So the first row of our matrix is going to have 3 columns corresponding to the first row times each of the 3 columns. The second row can multiply each of the 3 columns. So we're going to have a second row of the product matrix and 3 columns. So we're going to get a matrix with a first row, first column, first row, second column, first row, third column, because we can multiply first row by first column, first row by second, first row by third. And then the same with the second row times the first column, second row times the second column, second row times the third column. So I've indicated that between two brackets and with little X's here. And I'm going to write over when I get the numbers. And I'm not going to write out all the details. I'm just going to say them. Okay, the first row is 2, 3, 7. We multiply it by the column 1, 3, 2. Okay, so 2 times 1 is 2. 3 times 3 is 9. That makes 11. 7 times 2 is 14. 11 and 14 is 25. Now, if I did that wrong and you did it right, congratulations. Okay, I'm not going to check this. Just illustrating how it's done. Okay, then the 2, 3, 7 multiplied by the second column of the second matrix, 2, 1, 3. 2 times 2 is 4. 3 times 1 is 3. That makes 7. 7 times 3 is 21. 21 and 7 makes 28. Okay, then 2, 3, 7 times 3, 2, 1. 2 times 3 is 6. 3 times 2 is 6. That makes 12. 7 times 1 is 7. 12 and 7 is 19. Then, second row, first column, 4, 1, 5, multiplied by 1, 3, 2. 4 times 1 is 4. Negative 1 times 3 is negative 3. That makes 1. 5 times 2 is 10, so we've got 11. Second row, second column, 4 times 2 is 8. 4 times negative 1 is negative 1. That leaves us 7. 5 times 3 is 15. 15 and 7 is 22. Okay? Then 4, negative 1, 5 times the third column, 3, 2, 1. 4 times 3 is 12. Negative 1 times 2 is negative 2. 12 negative 2 is 10. And then 5 times 1 is 5, which added to 10 is 15. There's our matrix. Now you could write it out in more detail. You know, if you want to be able to check it, you would want to write out the 2 times for the first row, first column. You want to write out 2 times 1, 3 times 3, 7 times 2, and then do the arithmetic. I would not recommend just punching these into a calculator. Of course, most calculators will do matrix multiplication, but you want to do it by hand and you want to get the process firmly in your mind, okay? So that you can understand what these multiplications actually mean. And we'll talk about that in a minute. Okay, so we've seen how to multiply matrices. Why do we bother multiplying matrices? Well, there are a whole lot of reasons. And it's really, very, very important process. But one thing we do, we've seen how to solve a system of simultaneous equations using augmented matrices. We can also use matrix multiplication to solve a system of equations. Now, there's 2 steps to that. One is you represent the system of equations as a matrix product. The other is you do an inverse matrix, which involves making an augmented matrix and reducing it to a certain form. Okay? And that's not difficult, but it's a little tedious and hard to do it correctly every time. Okay, so let's just start with equations 2x plus 3y equals 7 and 4x minus 5y equals 13. Okay? Now that's a perfectly good system of equations. You know, you could write out an augmented matrix 2, 3, 7, 4, negative 5, 13, and reduce it. Okay, that's one thing you could do. We already know how to do that. We could also write this as a matrix product. Follow me here. We write the 2, 3, and the 4, negative 5 in a matrix. In other words, the coefficients of X and Y in the first equation go in the first row of the matrix. So we've got a matrix with first row 2, 3. Then the coefficients of X and Y in the second row become second row of our matrix. So 4x minus 5y gives us coefficients 4, negative 5. That's the second row of our matrix. Now we pull this neat little trick and multiply this matrix by xy. Well, how do we multiply a matrix by a column? First row times a column, second row times a column. How do we multiply a row times a column? First number in the first number in a row times the first number in the column, second number in the row times the second number in the column. Okay. So if we multiply out this matrix, and I'm not going to put that product next to the equal sign. I'm going to put that product down here. We're going to get 2, 3 times the first row, 2, 3 times the column x, y gives us 2 times x plus 3 times y. That's the first row of our product matrix. And of course, that's a 2x plus 3y of our original first equation. Then we multiply 4, negative 5, the row 4, negative 5, second row of our matrix, times the column. We're going to multiply 4 times x, negative 5 times y. Okay? So that we have everything to the left of the equal sign in our original equation is now in this matrix. Well, what goes to the right of the equal sign? Well, to the right of the equal sign, we're going to put 7, 13. In other words, the numbers on the right side of the equal sign. So first row, it's 2x plus 3y equals 7. We put that 7 in the first row of our column matrix on the right-hand side of the equal sign. And then we put the 13 for similar reasons, the right-hand side of the second equation. And now we have the matrix product, 2x plus 3y, for first row, 2x plus 3y, second row, 4x minus 5y equals column, first row, 7, second row, 13. So 2x plus 3y is first row of our left-hand matrix. 7 is the first row of our second matrix. In those matrices are equal, so the first row of this one has to equal the first row of that one. First row of the first matrix has to equal the first row of the second matrix. And similarly, second row of the first matrix has to equal the second row of the second matrix. So we come full circle. We started with the equation 2x plus 3y equals 7 and the equation 4x minus 5y equals 13. We've represented this system of equations in matrix form. Product of matrix with column vector equals another column vector. We worked it out, and then we wrote out what that means, and what that means is what we originally said. So we can go from this matrix representation of a system to the just system of simultaneous equations, or vice versa. The reason that's so powerful is there's this thing we can do called inverting a matrix. If we do the inverse of the 2, 3, 4, negative 5 matrix and multiply it by both sides, we just get the column vector x, y, and we get two numbers in a column on the right-hand side, and those are going to be the values of x and y. Now, you're not going to necessarily understand what I just said. I'm just telling you where this is going. And we might not even go there, but that's one reason we talk about matrices and matrix products. Computers handle matrix multiplication, reduction, et cetera, very, very efficiently. So they're used throughout. Now, there are other applied problems that have interpretations. And we talk some about those interpretations because that's probably most important for this course.